Welcome everybody to a presentation on chemical tests for ions in aqueous solutions. The first ion we will start with is the carbonate ion. The most common method for observing carbonate ions is to add hydrochloric acid to the solution. If effervescence occurs, then this gas should be bubbled through lime water to confirm it is CO2. The lime water should turn a creamy milky colour and will confirm carbonate ions were present in the starting solution. All the alkali metal carbonates are soluble in water. There is one alkali metal, however, that is an exception, and this is lithium due to its low solubility in water. The extremely low solubility is all due to lithium having a very small cation. This results in the electrostatic attraction between the Li cation and the carbonate ion being much stronger than between the water molecules. There are many different chemical tests that can completely identify all the different carbonate containing compounds, so a link has been provided at the bottom of this slide. The test for the alkali metal carbonates is the addition of barium or calcium chloride solution to the carbonate solution. These alkali earth metals are examples, but any alkali metal that is soluble in water which forms a solution will then make an insoluble alkali earth metal carbonate precipitate. This results in two precipitates forming, which are barium carbonate and calcium carbonate respectively. These precipitates will then dissolve when a weak acid is added to the solution. Another common method you may see is if the compound consists of metal and carbonate is to heat it so it decomposes. This will result in the metal oxide being formed and emission of CO2 gas. The next ion is the sulfate ions, which are another aqueous ion that can be identified via chemical tests. The first step is to add a few drops of HCl to acidify the solution. Then a few drops of barium chloride are added and a white precipitate of barium chloride should form if sulfate ions are present. Some issues with this are false positive results. If there are carbonate ions present in the starting solution, when the dilute HCl drops are added, a white precipitate will form, giving a false result. Barium nitrate can be used, but this would mean nitric acid needs to be used to acidify the starting solution. Sulfuric acid cannot be used as the sulfate ion is present in both, meaning no precipitate will form. Again, a link has been provided for more detail. The next ion is the nitrate ion. This is identified by reducing the ion to ammonia. The first step is adding NaOH to the starting solution. The next is the addition of aluminium powder. The aluminium powder will reduce this nitrate ion to the ammonium ion. Then the ammonium ion reacts with the hydroxide to produce ammonia gas and water. Damp blue litmus paper should be used to identify if ammonium gas is present. This will turn blue if the ammonia gas is emitted. It is key that with this test small quantities are used as ammonium gas is toxic, so larger volumes present will present a larger risk. A link is on the bottom of the slides to a website that will go slightly more in depth for each chemical test that I have spoken about.
Testing with silver nitrate identifies the three halide ions, the Bi- and the Br- in aqueous solution. The reaction creates a precipitate, which is a solid formed when two aqueous ions react together. This is the equation of the chlorine ion, but it is basically the same for the other two ions. This is a substitution reaction as the chlorine and the NO3 ion swaps positive ions, and the precipitate is formed from the AgCl. The method for obtaining this precipitate is you add a small amount of HNO3 to the solution to dilute the acid, then you add AgNO3 to the solution and the precipitate will be formed. The chloride ion shall produce a white precipitate, the bromine produces a cream precipitate, and the iodine produces a yellow precipitate. Here is an image of the precipitates. There is a further way you can test the halide ion, that is reacting it with NH3. Adding dilute ammonia to the solutions containing chlorine ions will cause the precipitate to dissolve, while solutions containing iodine and bromine ions will not dissolve. Adding concentrated ammonia to the solutions containing bromine ions will cause the precipitate to dissolve, while the solutions containing iodine ions will not dissolve. Iodine ions will not dissolve in any concentration of ammonia. The ammonia reacts with the silver from the precipitate to form this equation. This lowers the concentration of the silver ions. With concentrated ammonia, silver bromine pushes the reactions more to the right, increasing the amount of AgNH3
Another type of aqueous ion test is the flame test. It's an easy way of identifying metal ions because it's very simple to set up and the apparatus is very basic. The heat from the Bunsen burner causes electrons to be excited from the ground state to higher energy levels. When these electrons return to the ground state, light is emitted. We can observe this color. These are not all the ions that give a color when you heat it with a Bunsen burner, but they're most of the ones that are clear. There are a lot of issues with the test though. The flame could be affected by the fuel that's used for the Bunsen burner. They can't detect low concentrations of the ion, and common impurities like sodium can affect the flame color. There's no single color for all metal ions, so two metals might give off the same color, so it could be unclear which one of those is in the solution. The test is very simple, like I said. Electrons are excited from the ground state to high energy level. When they come back specific energy levels, they produce an emission spectrum. An example of this is sodium. The heat emitted by the flame is absorbed by the outer valence electron. Orange-yellow color is given off when the electron comes back down from a higher energy level to the 3s1 level. Sodium gives off a orange-yellow color, which is a short wavelength, as it has a stronger affinity for the outer electron. This means more energy is required to promote it to higher levels, and so when the electron comes back down to the ground state, it releases more energy than other metal ions would. Higher energy means shorter wavelength. The flame test is very simple, like I've said. All you have to do is heat a platinum or nichrome wire, inoculating loop, above the flame. You use platinum or nichrome because they're very unreactive, so they wouldn't give off a color if you were to heat them. You then dip the loop in the aqueous solution and safely hold the wire above the flame, and you observe the color.
In order for transition metal ions to be tested and therefore identified, the cations need to be in an aqueous solution. However, the metal ions cannot exist in isolation in aqueous solutions. They can only exist when bonded to ligands, which produces a complex ion. Ligands are the surrounding neutral molecules or ions bonded to the central transition metal atom. The ligands have at least one donor atom with an electron pair that is used to form covalent bonds with the central atom. This is an example of a complex with the central atom, the ligands, and their free electron pairs. These complexes in aqueous solutions result in differently colored solutions due to the activity of the ligands. Light is absorbed by the metal atom if the energy of the light matches the energy gap between two energy states within the atom. The effect of the ligand is that it causes the d orbitals in the transition metal atom to split into two separate orbitals, one of higher energy and one of lower energy, thus producing the two energy states needed for light to be absorbed by the atom. When light passes through the solution, a photon of light will be absorbed. The energy of this photon corresponds to the excitation of an electron from the lower energy level to the higher energy level. The size of the splitting of orbitals means that certain wavelengths of light are absorbed, causing the electron in the lower energy state to be promoted to the higher one. The remaining wavelengths of visible light are transmitted, causing the color of the solution. The wavelength of light absorbed depends on the energy difference between the two levels, and so will be different for each transition metal atom. Therefore, this will result in differently colored solutions for different transition metal atoms. This allows us to identify the metal atom in the complex. For example, an iron complex with 6 water molecules attached as ligands is a pale green color in solution. A copper complex, also with 6 water molecules attached, is a blue color in solution. Further tests can be done to confirm the transition metal atom. For example, the addition of hydroxide ions to the complexes. When 2 hydroxide ions are added to the iron complex, the product is a dirty green precipitate. Also, the addition of carbonate ions to the complexes. When a carbonate ion is added to the copper complex, solid copper carbonate forms as a blue precipitate. These tests allow us to confirm the identity of the transition metal ion. This is a link with more detail on other reactions with transition metal ions. To conclude this presentation, there are many different chemical tests to identify which aqueous ions are present in a given solution.